Hello, welcome back to the Royal Institution, and it's very nice to see familiar faces in the audience. As you know, the theme of these lectures is handedness. And we looked first at the handedness of man. And man turns out to be handed. He uses one hand in preference to the other. And he always has had. We could show that too. So far back as we could possibly remember or find out, he always has been. And we also suggested that his brain and its workings were all under chemical control. And the minute we talk about chemistry, we talk about molecules. And as we shall see, it is the control by handed molecules which is important. And so, in this lecture, we're going to look at the effects of handed molecules on us that arrive in our bodies from outside or are inside our bodies anyway, are innate to our structure. So, let's start with the effects of some molecules on us. Let's take a very familiar scene. Oranges and lemons say the bells of St. Clement's. But one thing that the bells of St. Clement's do not say to us is that there is a handed molecule in oranges and lemons. This is limonene, is its name. And in lemons, it occurs in its left-handed form. And in oranges, it occurs in its right-handed form. And so we are taking in right and left-handed molecules. These odors are familiar. Let's turn to another familiar situation. A nice steak here. Bryson is having to work very hard in this lecture, and so that's Bryson's dinner. I'm allowed to have the bottle of skimmed milk. The point is that steak contains an acid called lactic acid. It actually gets its name from the bottle of milk. And in the bottle of milk is left-handed lactic acid. In the steak is right-handed lactic acid. And so if you both of these, you're taking two versions of one molecule, the right-handed version and the left-handed version. Now, how do we recognize these as being different? How do we recognize the different smells of oranges and lemons? How do we do that? Well, we have detectors. And these must be handed detectors. So let me just show you that. If I can have a volunteer, please. Would you like to come out and join me? Thank you very much. It's very good. What's your name?
Nick.
Nick. Okay, Nick. I'll tell you what we're going to do. What we've got here, you'll be astonished to learn, is a whole lot of molecules. Now, you're going to say, well, they're not actually molecules. They're really gloves. But they're left-handed and right-handed gloves. Get it? Now, here's a very simple experiment. I'm just going to blindfold you. Right? It's absolutely painless, like all the experiments in this demonstration. All right, we'll tie that round you. That's good. I think we've got that right. Are you comfortable?
Yep.
Good. Right. Now, I'm going to give you a pair of non-handed detectors. Okay, just hold that there. All it is a pair of tongs. Can you feel that? No, put your fingers in there. Can you feel that? All that is a pair of tongs. Probably used those at school. Okay. Can you feel? Right. Now. Okay. Are you all operating? Right. Now, all I want you to do is just pull me out a left-handed glove and a right-handed glove. Can you do that? Have a go. See what you get. All right. Use them. Right. Okay. Now, which handedness have you pulled out for me? You got a 50-50 chance of being right. Okay. He got it right. Yes, just by an accident. Okay. Have another go. Have another go. See if you can pull out there. Okay. What do you think you've got there?
Another left.
Another left. Very good. Have one more go. What do you think you got there?
A right.
A right. Wrong. Okay. What you've done is to pull 3. Right. Okay. Now, you didn't have any handedness there. Now we're going to give you a pair of handed detectors. And Nick has had these detectors for, I should think, about, what, 12 years or so?
Yes.
Right. Okay. Have a go now and choose a pair. All right? And let's see how you're going to do that. How are you going to tell if that's left or right? How are you going to tell? That's good. Try your hand in it and see if it fits. See which hand is going. Okay. So what handedness is that one?
Left-handed.
That's left-handed. All right. Now see if you can find a right-handed one. Yep. All right. Try that one. Doing very well, actually, when he puts them on the right way around. Right?
Yeah,
What handedness is that one, then?
that's right-handed.
That's right. Okay, I'm going to release you now. Right? Very good. Thanks very much for coming to help us. And get rid of those now. Now, that's a very, very simple experiment. But it shows us straight away that if you're going to recognize handedness, you need to be handed yourself. You can't do it unless you've got handedness recognizing handedness. Fine. Now, it's all very say hands are detectors, and of course he's got handed detectors, Nick. Fine. But let us just look at another sensation which has got a handedness component. Right? Now, can I have a volunteer, please? Will you come down? Thank you very much. What's your name?
Richard.
Richard. Thank you very much for coming to help us. Right. Now, what we've got here, okay, what we've got here, and I'm just going to put them around that way, that's good. Okay, what we've got here now are, in these orange bottles, we've got a molecule, one molecule. It's called a carvone. And in these blue bottles, we've got the same molecule, still called carvone, but in this pair of bottles, it's spearmint, actually. It's the right-handed carvone, and that is responsible for the smell of spearmint, okay? And in these bottles, the carvone, which is left-handed, is responsible for the smell of caraway seeds. Right. Okay, now we're going to see if you can tell the difference. Okay. Now again, it's all blindfolded, so there's positively no cheating. It's very important not to cheat in science. Okay, very important. Now, I'm going to put a bottle under your nose, and then I want you to tell me, can you recognize that smell?
Yeah.
What is that smell?
Spearmint.
It's spearmint. Right. See if you can recognize this smell. Is this the same or different?
It's different.
It's different. That's the other one. So that's left. Notice how the experiment is being conducted, please. Right. Positively no cheating. What do you think of that one?
It's left.
That's left. And so this one, what do you think of that one?
It's right.
It's right. Okay. Good. Thank you very much indeed for coming. Thank you. And so what we've seen happening here is that Richard's nose could tell the difference between the right-handed and the left-handed versions of the same molecule. And to do that, the detectors in his nose are able to tell the difference between right and left. And that tells us a very simple but very profound fact, that his detection mechanism, like all of ours, is handed. It's actually done by having a handed giant molecule, but that's a later story. Right. Now let's think what the effects of other handed molecules in our bodies are. And I want to introduce you to a very important set of molecules, and these are called the hormones. And if I can have a volunteer, please. Thank you very much. What's your name? Hayley. Hayley. Thank you very much for joining us. Would you like just to sit there? Right. We're just going to illustrate now the effect of hormone release on Hayley. Now, it's absolutely painless. What we're going to do is measure your heart rate, okay? And we can measure your heart rate with a very sophisticated piece of equipment here. When I can remember how to work it. Yes, there we go. Now, will you just put your index finger out. Just point at the audience. I think we'll take your index finger. Yes, that's all right. That's fine. Okay. And you can hear that peeping, all right? And soon we're going to get a read of Hayley's heart rate. And here she is. Her heart rate's about 9900. She's under a little bit of pressure, being pulled out of the audience to do experiments and all the rest of it. It's quite normal. Okay, fine. Okay. We're making you laugh too, and that's bad. That's bad for your heart rate. Okay. But you're settling down about 109. Now, I've got Dr. Bryson Gore here, and he's just going to do a tiny little experiment. I mean, it's just is completely painless. And what he's going to do is, you see, you've probably seen this sort of thing before. And notice that our heart rate went down to 86. All right, so just put out your hand. We'll just give you a little swab there. That's very good. Okay. Fine. Are you ready? I think probably we've done enough. Thank you very much for coming. We'll spare you the horrors of being injected, and we wouldn't really trust Bryce in any case. Thanks ever so much for coming. Thank you. What we saw there, it wasn't very dramatic, but Hayley's heart rate went down to about 86. When she saw the needle, it was going back over 100. In fact, coming down to do the experiment turned out to be more stressful than the prospect of being injected. But no matter, what we're seeing here is, in a sense, in both demonstrations, just calling down Hayley alone was enough to upset her heartbeat. Now think what that is doing. What is happening here is that when Hayley, I called her down, just as when I came into the lecture theatre. What happened was my heart was going faster and Hayley's heart was going faster. And what was happening there was that a handed molecule called adrenaline was being released from the adrenal glands just above her kidneys into her bloodstream. And that was spread all over her body, including her heart. And the message was, we're under pressure. We've got to do something. I want higher blood pressure so that my muscles are more effective. And if I need to fight, I can fight more bravely. Or if I need to run, I can run away faster. And you can see that that's a very important protective mechanism. It's the fight or flight reaction. Now I want to come on to a different topic, and that is sex. Right. Now, sex is in the title. Okay? And of course, sex is a very important matter. And it, again, is controlled by hormones. Let us just think of the point of sex for a moment. We are mammals, and the mammals are the most successful species on the surface of the Earth. They've beaten the dinosaurs, for example. Why is that? It's because they're warm-blooded, and so they can adapt to a whole range of different environments. You can have a polar bear and a camel, for example, living at the North Pole and at the equator. Okay? So they're very adaptable and very successful. Now, how do they arrange this? Well, they arrange this with sex. Simple as that, and sex is a matter of chemistry. I'm trying to plant in your minds, of course, the fact that everything is a matter of chemistry, but that's another matter. Okay, testosterone is the male hormone. And testosterone is released into the bloodstream of males, and it has the following effects. First of all, it makes them grow facial hair, which is a blinking nuisance, and it makes their voices go deeper, and it makes them grow big muscles. That's the reason why men are bigger on average than women. It's because of testosterone is a muscle builder. For women, the hormone is called estrone. And remember what the role of a woman is, it's got to rear children. And so estrone releases eggs from the ovary. And so this is a very, very important biological matter. And of course, it's very successful in survival. What these sex hormones are really doing is carrying the message of the instruction book for our lives, that's DNA, which we shall see tomorrow, carrying the instructions from DNA, putting the instructions into effect, and that makes a very good survival strategy. So that's where sex comes in terms of these handed molecules, both testosterone and estrone. These are handed molecules. Our lives are in the hands of handed molecules. Right, now let's turn to a different matter. And I should say, just to finish off the little piece on sex, that it is important that these steroids, both testosterone and estrone, belong to the steroids. And it's important that these should not be abused. Some athletes mistakenly take testosterone, for example, for muscle building. That's a great mistake because it upsets the sexual balance and it makes the person who takes them very aggressive because that's part of the hormonal result of this matter. Right, let's go on to another matter. What about archaeology? Right. Alas, poor Yorick. I knew him well, but in Yorick's teeth, they're covered with dentine, right? Protective, very hard, long-lasting. Of course, in human remains, the teeth last very, very well. And so they're very important from the point of knowing what's gone on. And in the dentine of teeth is a handed molecule called aspartic acid. But aspartic acid changes its handedness with time. Let me illustrate this for you. Here we have a graph which shows the fact that when we're born, this is a picture of me as a baby, when we're born, we have entirely, or virtually entirely, left-handed aspartic acid in our teeth, if we have any teeth when we're born. But as we get older and older, then part of our left-handed aspartic acid turns into right-handed aspartic acid, and this graph shows the change. But this change from left to right goes on after we're dead. And it goes on, it can go on for hundreds of years. And the value of that piece of information is that we can tell the age of, for example, skulls from their teeth after several hundred years. And that's actually very useful archaeologically because it's very easy to tell the age of skulls if they're tens of thousands of years old, but it's much more difficult. That's done by radiocarbon dating, which you'll have heard of. But if they're only a few hundred years old, that's much, much more difficult because radiocarbon dating doesn't work, and the aspartic acid, however, gives us a very good age. And, for example, the date of a Japanese burial mound can be accurately put to the 9th century by measuring the amount of change of left to right-handed aspartic acid in the teeth of the skeleton there. So, not merely do you get a smile from a skull, but you get information as well. All right, now, let us think about outsider molecules. All the molecules that we've talked about so far are insiders. Let's talk about outsiders. Now, at this stage of a lecture, you often feel a bit peckish, and so I thought I'd have a little bit of Japanese food, and we're very lucky to have a very elegant waiter here looking after us. What style? You only get this sort of style in the Royal Institution. They have an excellent restaurant here, and I got a little dish of pot noodles, and I'll just have a couple of mouthfuls with my chopsticks. I don't want to fiddle about actually with the Japanese food. What is important here is the soy sauce. Okay. Soy sauce. Now, soy sauce is added to Oriental food, and it makes it taste delicious. Indeed, the very word is umami in Japanese. It's just one of the many Japanese words that I know. That's one of the four. Okay, so that is, it's delicious. It makes the food taste delicious. It doesn't actually taste of anything itself. Now, the food freaks say, well, you don't want to have all these terrible chemical additives. Notice that food freaks use chemical as a dirty word. You notice that? Right. Food freaks would say you mustn't add these chemicals to your food. But that's baloney. Because in soy sauce, the stuff, the active ingredient, as they say, is monosodium glutamate, of which you've all heard. And that glutamic acid is part of the proteins from which we're made. And so we're just taking on a little bit more of what we've got already. Right, now, so much for Oriental food. Let's just go back a little bit in time, 200 years, to the beginning of chemistry. And at this time, there were explorers like Captain Cook, and botanists like Captain Bligh. Now, you've heard of Captain Bligh, the captain of the Bounty. Now, Captain Bligh was a botanist. And both he and his contemporary, James Cook, were fellows of the Royal Society. And what Captain Bligh did was to sail all over the Pacific, and he was interested in the possibility of moving plants. And he moved plants from, for example, Tahiti to the West Indies. But he was a tough chap, Captain Bligh, and the holds of his ship, you see, the Bounty, were full of plants. And he was very keen that they should survive, and he watered the plants more than he watered the sailors, and in the end they'd had enough, and we had the mutiny on the Bounty. And so here's Captain Bligh being put in an open boat in the middle of the Pacific. But what he had done was to move a very important plant. He moved the breadfruit plant from Tahiti to the West Indies. Here's the breadfruit, and there it is, lovely plant, full of starch. And that's now a staple diet in the West Indies. But there was another plant that Captain Bligh moved. And this plant was called the ackee plant. It was actually called after him. Its botanical name is Blahia sapida. And here it is. Here's the ackee fruit. It looks very delicious. And we've got another picture of it. Here it is. Give you a scale. See, look, a lovely black fruit there. But there's a problem with this ackee, and that is this, that children in the West Indies are tempted to eat the ackee fruit when it's not ripe. And in the ackee fruit is a poison. It's a little handed molecule. And this little handed molecule gives a link between Captain Bligh and my research laboratories in Sheffield. Because what this little poison molecule does, when children eat it, it depresses their blood glucose level. We're always hearing about glucose because it's very much part of the stuff of life. But it depresses the glucose level in the body, and children may die unless they're treated. But you can treat a child who's affected just by giving them glucose, and that puts their blood glucose back again. When the fruit is ripe, it's very, very good. Now, what is happening in this process is that the blood glucose falls because the little poisonous molecule stops the production of glucose in the body. And so that's a very, very important matter. And in Sheffield, I'm collaborating with biochemists. My colleague, Dr. Paul Engel, is an expert on enzymology, and we are working to try and find out how it is that this little handed molecule can cut down the glucose. It's blocking the glucose-making factory. Right, now let's take another poison which is very, very familiar to you all. And that's nicotine. Nicotine, which is present in the tobacco plant. And nicotine is a little poisonous handed molecule. There it is. That just breaks like that, and you can see, of course, the tobacco leaf. I hope, of course, that none of you smoke. Well, let me just give you a little illustration of smoking. What we've got here is a sort of smoking machine. It's a Bryson special, and Bryson is going to smoke that cigarette for you very quickly. Let's see what a smoking machine consists of. When I can say the word, it consists of a pair of lips, a throat, and your lungs, right? When we look at the smoke going into your lungs, right? So when you have a fag, that's what's happening inside you, right? Notice how fast it's being smoked. Notice another thing that's happening here. Do you see here, down near the tap here, all the brown tar from the cigarette is condensing and running down. And that could be your lungs, okay? Now, you all know, of course, that smoking gives you lung cancer. And the reason for that is that all this tar goes into your lungs, and the carcinogenic, that's the cancer-making chemicals in tar, give you lung cancer. But not merely do you inhale all this smoke, but you inhale nicotine in the tobacco smoke. And nicotine is a little handed poison. And what it does is that it increases your heart rate, and it damages your liver. And both of these are bad. But worst of all, it's habit forming. It makes you want to go on smoking. And so you go round the cycle of having another fag and another